Good morning, boys and girls, and welcome back. Today we're going to start our talk moving on from sequences to series now and series convergence. So let's talk about a little review of summation notation. If you remember from pre-calc, summation notation starts with a sigma here. The n equals, or sometimes I equals on the bottom is where you were starting to plug in to add, and then the number on top is where you're going to stop. So in this case, I'm going to start plugging in at 1, and I'm going to keep plugging into infinity. And what I'm going to plug into in this case is 1 over 2 to the n. All right? So what this now represents is this series here. If I plug in 1, I get 1/2. If I plug in 2, I get 1/4. If I plug in 3, 2 to the third is 8, 4, 16, so on. And this... again, the summation notation means to add these all together, which gives me a series versus the sequence again. Right? Now, our question is going to be, face something like this. Hey, does this series converge? Throughout a lot of this unit, we're going to talk about the convergence of series and trying to figure out, do series converge? And we're going to talk about a lot of tests that do that. In this case, sometimes they're going to ask us what is the sum of the series? And that becomes a lot harder question. In this case, we're going to try to answer it for this series in particular. But there's not very many ways we have to find the sum of a series. But to see if this series converges, and to play around a little bit, and to find the sum, we can do what we call partial sums. Partial sums is where we are going to start adding up the terms and just see like what we get to. So S1 in this case indicates, hey, this is just the sum of the first term. And so the sum of the first term in this instance is 1/2. And then S2 would be the sum of the first two terms, which is 1/2 plus 1/4. And that gives us 3/4. S3 is going to be the sum of the first three terms. And if we add the first three terms together, I get 7/8. And then I'm going to now find the sum of the first four terms. All right, and so now what we can do with partial sums is we can create a new sequence of the sums that we have just found. And now we can ask ourselves, yesterday's question, will this sequence converge? If this is the sequence of sums, and if that sequence converges, then the sum would converge. So what I'd want to do is go and write the explicit formula for this sequence. In this case, it would be 2 to the n minus 1. If we notice, on the bottom is 2 to the n, 2, then 2 to the second, 2 to the third, 2 to the fourth. It's 2 to the n. And then the top is always just 1 less than that. 2 minus 1, 4 minus 1, 8 minus 1. So our explicit formula is 2 to the n minus 1. And if I take that limit as we go to infinity, the minus 1 doesn't really matter, and this becomes just 2 to the n over 2 to the n. And so, yes, this is going to converge, and it would converge to 1. Okay? So the sum of this series would be 1. That's pretty cool. So, bottom line here is, if the sequence of partial sums converges, then the series is also said to converge. Let me write that down. So, if the sequence of partial sums converges, then the series is said to converge. And this is really like one of the main ways that we have to find the sum of a series. All right? We won't do this again a bunch. It's very hard to do this sometimes, to that whole process there, to write your explicit formula and everything. But if I was going to try to find the sum of a series, this is one of the main methods we would use. All right, on to another method we have, though, using geometric series. All right, a geometric series, again, is a series where the terms in the sequence, we're multiplying by a ratio common factor to get from one term to the next. The series we just were playing around with, 1/2 plus 1/4 plus 1/8 plus 1/16 is a geometric series, because to get from term to term, I'm multiplying the previous term by 1/2, and that would get me to the next term. So this is a geometric series, and 1/2 is the R value right here. That is your common ratio. A is just any constant, could be anything. And so it's written in this form, or you can write it in this form. The sequence we had before was 1 over 2 to the n, which I could write as 1/2, and again, there's our common ratio, to the nth power, that is the same thing. And so I can see that this is a geometric series. When you have a geometric series, if the r is absolute of r is less than 1, can't be equal to 1, it's got to be less than 1, then the series will converge. And if the series does converge, then you can use this formula right here to find the sum of the series, where a sub 1 is the first term, 1 minus r, and r is that common ratio. And that formula will work. If it asks you to find the sum of a series, this is the first thing I would look for because it is the most common thing we use to find the sum of the series. See if it's a geometric series and start there. If not, then you might look at partial sums, or we'll talk about some other methods as well here in a short sec. All right, we're going to pick up our first test for convergence, which says that if a series converges, then the limit as n goes to infinity of the sequence is going to equal 0. Okay? If I look at the terms in the series, if those go to 0, if the series converges, then those terms are going to go to 0. I had to stop myself there and be careful because the converse of that is not true. Just because the terms go to 0 doesn't necessarily mean that the series will converge, okay? But if the series does converge, then the terms will go to 0, all right? This is called the nth term test for convergence. However, the way we're really going to use this, because again, like I said, it's not, the converse is not always true, is we really use the contrapositive as a test for divergence. And here's what I mean. This is not really called the nth term test for divergence, but this is what I refer to it as. And this contrapositive idea, and this we use quite a bit. This should be the first thing when you check for convergence. You should run this test first, the test for actually divergence, which says that if the terms do not go to 0, if the sequence does not go to 0, then the series is going to have to diverge. Okay? So if the series converges, then the terms will go to 0. Just because they go to 0 doesn't mean it converges. But if the terms don't go to 0, then we do know that it diverges. Clear as mud, huh? All right. So let's play with this a little bit with some series. I'm going to give you some, and we're going to see, do they converge, or can we tell if they converge or diverge, or what can we tell about them? So here's our first series, and I found it very helpful, especially in the beginning when I first started playing around with this stuff. I think you want to maybe try to write the first few terms out just to kind of so you can see what's going on with this a little bit better, make things a little bit more tangible. So in this case, you can see here that this would be 2 to the 0, because we're starting at 0, plus 2 to the first, plus 2 to the second, plus 2 to the third, all the way to infinity. Or this series would be 1 plus 2 plus 4 plus 8. And so now that we kind of play around this, we can see, again, that this is going to fail the nth term test for convergence, or it passes the nth term test for divergence. Because the limit as n goes to infinity of 2 to the n, because this is going to go to infinity as it gets bigger and bigger, it doesn't go to 0, I know that this has to diverge. Technically because it fails the nth term test for convergence. Okay, so again, here is another series. We want to see if this one's going to converge or diverge. You could, again, write out the first few terms. And if I did, I would get something that kind of looks like this. And this one, not as easy to tell if this one's going to converge or diverge. So again, you generally are going to want to end up looking at this limit. The limit as n goes to infinity of n factorial over 2n factorial plus 1. And now, because we're going to infinity, that plus 1 would disappear. And then the n factorials could cancel out. And so we can see that this thing is going to go to 1/2. Now again, because it's going to go to 1/2 and not 0, this fails the nth term test for convergence, and therefore I know that this is going to diverge. Okay? If it converged, that would have to be 0. Okay, and here's another one. The series of 1 over n. Again, maybe right at the first few terms. Again, you don't have to do that part, but again, I really found it helped me when I first started dealing with all this series stuff. In this case, it looks like it's going to 0, so let's look at the limit. And if we look at the limit, we can see that this is going to go to 0. So what does that tell us? Hopefully you didn't tell us that tells us that it converges, okay? Just because it goes to 0 doesn't mean that it converges. It means it could converge, we don't know. And that's why I really view this as a test for divergence. If it doesn't equal 0, then it diverges. If it equals 0, now it could converge, so I'm gonna have to go on to other tests down the road. All right? But the test for nth term test for convergence / divergence, you're really going to test to see if it diverges and get rid of all those ones that diverge. And if it potentially could converge, we are now going to do more tests on it. So this test does not show convergence or divergence if it equals 0. Okay? We're now kind of back in limbo. We don't exactly know what's happening. Now on the next one here, as we look at this one, I guess I could, apply the nth term test for, convergence, divergence on this thing. However, I should note there's in a slightly different form, and you want to start to be able to recognize this form. This one is actually a geometric series, right? Our AR to the K, or AR to the N. So I don't really need to apply the nth term test for convergence here. I can just go ahead and look at my R value. And we said, again, if R is absolute value of R is less than or equal to 1, it converges. But in this case, the absolute value of R, negative 1.03, is bigger than 1. So then this thing must diverge. Okay, so again, we have different kinds of series we're going to have to look at and be able to identify. So what I'm going to advise you to do is pause the video right now and try to work this one out on your own. Do you think this series is going to converge or diverge? Write out a few terms if you want to, but think about it, pause it, come up with your answer, and then you can check your work. Alright, so in this case, again, I started out by applying the nth term test for convergence and looking at the limit as n goes to infinity. Because it's going to infinity, I don't care about the plus 3, and so I get 1/2. And again, because this does not equal 0, it fails the nth term test for convergence, and so I know it must diverge. Alright, hopefully you came up with that same answer. Alright, on the next one, they want us to find the sum of the convergent series. So they're telling me it converges, I just need to find the sum. Whenever they say find the sum, though, again, we should be looking, we just talked about this a problem or two ago, but this is a geometric series. It's in that geometric series form. And my R is less than 1, so I can confirm that it is going to converge. I now just need to find the sum using our little formula. The sum is the first term over 1 minus that common ratio. When you find the first term, you got to pay attention to what you're plugging in to begin with. So in this case, I'm going to plug in 0. So when you plug in 0, that becomes 1. So my first term is 6 over 1 minus the common ratio 4/5. And when I work this out, I get 6 divided by 1/5, or 6 times 5, which gives me 30. So the sum of this series is going to equal 30. All right, next one, we want to find the values of x for which this series is going to converge. And then we're going to write the sum as a function of x. So again, hopefully we recognize that because I've got 3x to the n, that this is going to be a geometric series. And so I know this is only going to converge when r is less than 1. Or I should say when the absolute value of r is less than 1. And now I want to solve this absolute value inequality. Remember, to solve an absolute value inequality, you need to set up your case 1, case 2. Case 1, you drop the absolute value signs. Case 2, you drop them and change inequality and change the sign. So this would converge when x is any value between negative 1/3 and positive 1/3. Now I need to write the sum as a function of x. So if I plug in 1, the first term would be 3x, and our ratio would be 3x. So here is the sum written as a function of x. Okay, with my last minute here, I'm going to try to show you one more example of something that's not on the AP exam, but it is a cool way we can find the sum of a series sometimes, and they're called telescoping series. I'm going to write the terms of this out, and so we can kind of see what's happening with this series. So if I plug in 1, 2, and 3, this gives me the first 3 terms, or first 3 bits of this series here. And now you might be able to see what happens if I do a little regrouping. You can see when I group my terms that a lot of these terms are going to kill each other off. 1/2 will kill off 1/2, 1/3 kill off 1/3, and so on, really just leaving me with these 2 terms. The 1 in front and the minus 1 over n plus 1 in the back. So because we're going to infinity here, we can take the limit and look as we go to infinity, and we see that this is going to go to 1. And therefore the sum of this series is 1. Alright, thanks boys and girls. See you again.